Hey everyone. So what I'd like to do is to go over an AP problem. This is AP 2006-3. It's from your AP booklet, and I believe it is on page 5. So if you could turn to page 5, let's take a look at this one together. If you need to, pause it. If not, we're going to keep going. All right, here we go. So before I even begin, I notice it's a number line problem. All right, I got this. So it says 2-point charges, Q1 and Q2, are placed 0.3 meters apart on the x-axis as shown in the figure above. Charge Q1 has a value of -3 times 10 to the minus 9 coulombs. Ooh, that's nanocoulombs. The net electric field at point P is 0? Okay. Now, before I begin, I always kind of try to give a glance of the whole problem. First, it's asking about the sign. Then calculate the magnitude of the charge. Then calculate the electric force. Determine on a point where the two charges where the electric potential is electric potential. And then how much work. Okay. So I just gave it a quick glance. I know that I'm going to have to do forces, voltage, and work in this problem. Okay. All right. With more experience, you'll see right away where that's going to take us. So it says that the electric field at point P right here is 0. Now, charge 1 is a negative charge. So what direction would the field line point at point P relative to the first charge? It's going to point to the right. I would label that E from charge 1. Field lines point towards the negative charge. Now it says that the electric field at point P is 0. So obviously, what direction does the field have to point from charge 2? Yeah, it's got to point in the opposite direction. And it's going to be equal in magnitude, but opposite in direction. Now, if Q2 is creating a field that points away, what must its charge be? Yeah, that's right. Good. It's going to be a positive charge. To justify your answer, I'm sure you would write something much better, cleaner handwriting than I have. But I'm going to go with, since the shorthand I use there, first of all, I love this if-then statement. And this just means therefore. Pretty simple sentence structure. I write simply. Now, B says calculate the magnitude of charge Q2. Well, given the information that I have in this problem, I know that at that point, the sum of the electric fields is going to be 0. And because it's a field, I'm going to make it a vector and make it positive, point to the right. Now, that's going to tell me that I have plus E1 minus E2 equals 0. And I have a feeling you already knew that these electric fields were equal and opposite. All right, cool. Now, for a point charge, we know a formula for electric field. KQ1 over R1 squared equals KQ2 over R2 squared. Do we know what the R's are? Now, this is when I don't lose my focus. It appears that each one of these lines is equal to 0.1. So the distance for charge 1, R1, looks to me like it's going to be 0.20 meters. What do you think? Now, the negative sign I do not include. That is given in the direction of the vector. Now Q2, wait, is that 0.2? Who else besides Emma caught that? It's not 0.2. It's at 0.2, but Q1 is at negative 0.1. So this R1 is simply 0.10 meters. R2, you see it? R2 is going to be 0.4 meters. Now, here's the thing. I know that many of you are much smarter than I am, and you saw that right away. Doesn't it feel good to be smarter? The rest of you, you're like me. Next. To not lose focus, let's go back. K's cancel out. Good, I don't feel like dealing with that. Let's see what numbers I have. Q1 was going to be 3 times 10 to the minus 9 over 0.1 squared equals Q2 over 0.4 squared. Now, because I'm an experienced teacher and I hate dealing with all those scientific notation, I'm going to call that 3 nanocoulombs, and I'll just carry the nano through. Now, here's the part. It's tricky. There is no negative sign there because the sign was given by the direction of the vector. Okay? At this point, it's just math. And I'll be quiet for a moment. I almost did that in my head, and I likely would have made a mistake because of the squared, but I did the math out, and Q2 is equal to 48 newtons per coulomb. Now, before I move on from that, I got to look and say, does that make sense? Okay. So the 3 nanocoulomb charge is much, much closer than Q2. So if this is 3 nanocoulombs and it's 0.1 away, this would be 48 nanocoulombs, but it's 0.4 away. Since we have to square those values, yeah, I see it. All I was doing there is I was double checking to make sure my answer made sense. Okay, moving on. Calculate the magnitude of the electric force on Q2 and indicate its direction. Well, there is no charge at P, so the force between Q1 and Q2 is actually very easy to solve for. I'm going to have K Q1 Q2 over R squared. Now, normally, a number line problem, you would find the electric field at a point, put a charge there, and then plug it in. But this one's actually getting a little easier there. So to find the force, K is that constant, 9 times 10 to the 9th. Q1 was 3 times 10 to the minus 9. Q2 was 48 times 10 to the minus 9. And then how far apart are Q1 and Q2? Oh, that distance. See, they're trying to trick you. But they didn't get you, did they? That's going to be 0.3 squared. Now, my old math teacher would be very depressed if they saw me reaching for my calculator here. It's a weakness. Why don't you go ahead and solve that in your head? Go ahead. Ryan, I know you already have the answer in your head. Good for you. but I don't want to mess this up. Oh, man. I hope I can edit this video later. If I don't, it's painful. That's what I got. 1.44 times 10 to the minus fifth newtons. Moving on. Determine the x coordinate on the line, on the point, on the line between the two charges where the electric potential is 0. Aha. Nice. So what we have here, I'm going to draw another picture. If that's all right with you. I have Q1, which is negative 3 nanocoulombs. And over here, I have a positive 48 nanocoulombs. And if I were graphing voltage, I always try to sort of visualize this as a graph. My 48 Newton per Coulomb, as we got closer, it would actually start to go up to infinity. But because it's not an exact point charge, I usually will draw a little plateau there. The minus 3, that potential is not going to be as negative because it's smaller. So at some point, that line is going to come, it's going to curl down and cross. And then here's the kicker. It's actually going to come back over again because that 48 nanocoulomb is so much stronger. Over on this side, it'll never cross the x-axis. But the question asked, what point in between the two charges did that occur? So I'm going to let this distance be r, and this distance would be 0.3 minus r. Now watch what happens. Before you start crying, realize this is way easier than electric fields. The sum of the volts at some point in between is equal to 0. Now okay, wake up. Potential is a scalar. So because it's a scalar, all I have to do is include the signs and add them up. That symbol right there, sum of, just means add them up. So I'm going to write it as plus V1 plus V2 equals 0. So KQ1 over R1 plus KQ2 over R2. Now, the values, well, I'm looking, R2. What could I plug in for that? That's right, I just found it. 0.3 minus R. So if I go ahead, now careful, I'm going to, what am I going to do? Cleanest way might be this. K Q1 over R1 equals, I'm going to subtract it over to the other side. Oh, wait, that's just algebra. You got that. K's cancel out. Look at my values. 3 nanocoulombs over R equals wait. That's right. Negative 3 nanocoulombs over R equals negative 48 nanocoulombs over 0.3 minus R. All right. Oh, nanocoulombs goes away. Let's cross multiple. Oh, the negative signs go away. I'm not going to cross them off on my work here, but I got 3. Good. Keep going if you haven't already done so. I got 0.081 meters, but that's from Q1. Determine the x-coordinate of the point. Q1 is at 0.1, negative 0.1. So it appears to me that the point is at negative 0.1 minus, no, plus that. I got negative 0.082 meters. Now, if you thought that was the answer when you first looked at it, you're lying. No, you're brilliant. Now, put your pencil down. Take a deep breath. Just because you try a problem and it leads you to a place you don't think it's going doesn't mean it's wrong. You followed every step correctly. Knock on wood. And if you do that, you can trust your answer. Now, normally, then we'd ask everybody around here, what did you get? What did you get? Hopefully, that's the right answer. We don't know. But I do know that I showed my work really well, so that if someone were to look at my work, they could locate where any errors occurred. I don't know. I don't know if that's right. In the past, I think I've messed this problem up. Okay, if I was to take an electron from really, really far away, when it's at infinity, what would the potential be caused by these two charges? Yeah, it would be 0. And if I bring it from this really far away spot at infinity, where the potential is 0, to keep this simple, let's go to our formula. The work done by an external force would be equal to the charge times the change in potential. Now, if the change in potential is 0, it doesn't matter what path you take. If you're starting at sea level and you go uphill and down through a tunnel, but in the end you end up back at sea level, your change in height overall is 0. The same is true for electric potential. So if the change in potential is 0, the external, there it is. All right, you guys. Thanks.